Okay. All right. So I want to do kind of a wrap up on everything here today. Oh boy. I don't know what happened. Hang on. Hang on. There we go. All right. Okay. All right. So kind of a wrap up here on complex numbers. So this is our topic again. We start next week with differential equations on Monday. All the relevant sections in the book are there. All right. So if you're looking for the integration stuff that I talked about at the end, section 4.8's got a whole bunch of stuff on that. All right. But I want to make sure we kind of review real quick on everything. So I've tried to put together, I had this in the first set of slides on complex numbers, but wanted to put a quick summary in there so everything was in one clear place for you. All right. So you should be familiar with all of this stuff. So how do I go through and how do I calculate the magnitude, the angle? All right, what is the real part? What is the imaginary part? If I give you A plus JB, what's the imaginary part of A plus JB? B, not JB. All right. Some of you are going to get that wrong. All right. It's the coefficient on the J. All right. The other thing that might screw you up is this angle thing. Okay. All right. So that's one thing that you want to be mindful of. The addition and subtraction stuff. I tried to get this summarized here for you as well, and as well as the multiplication division. All the MATLAB stuff is kind of summarized here in terms of what commands to use in MATLAB. There's a couple of pages of those. The one thing that I have here for you guys to remember, which is the one thing that screws up everybody, right, is for all trig functions, right? If I have cosine omega t plus phi, by definition, what units is that in? Radians. Omega has what units? Radians per second, by definition. All right, so if you have omega t, if I have 300 t plus 30 degrees, it is kind of confusing because this 300 times t is going to be in units of radians, and 30 degrees is going to be in units of degrees. So you're going to have to do a unit conversion there. All right. I know for problem 5 that might have caused some problems for some of you guys.
If we were to accidentally not do that, would you get partial stuff?
That's my least favorite question in the world. Yes, probably. What's tricky though, what gets real tricky with this whole partial credit business is as time is dwindling down, I begin to see all the stuff where the words are going around the bottom of the page and there's an arrow to that page. So it needs to be clear, right? That's one thing I also like about giving them to you guys at home is you generally give me something a little bit more organized because you're not as rushed. Make sure it's organized. If I can't tell what the hell's going on, then yeah, it's tough, right? But if I can tell, then yeah, it's a different story. Okay. All right. So this is really important. Everything in MATLAB expects it to be in radians. All right. I've said that a number of times. You need to bear that in mind. All right. One other thing I wanted to make sure, this is on that other slide, but I put together here in one slide just kind of a quick summary of everything that I kind of consider to be a relationship that's from Euler's identity. Euler's identity is this top guy here. If I have a complex number, r e to the j theta, it's that. All right. R cosine theta plus j times r sine theta. All right. Now, what comes from that are these two relationships, cosine and sine, right? We don't need to worry too much about how to derive those two things, but you should know that they exist. All right. In my mind, stuff like what's on this page here should become second nature to you without needing a cheat sheet. All right. And at a minimum, that top one there, the one that I put in the red box, should become second nature to you as well. I don't expect that the cosine equals that and the sine equals that. I don't expect those to become second nature to you, but I do expect that first one to become that way. You should really know that. You're going to use it in many, many classes from here on out. All right. Important thing I also wanted to make clear is the real part of any complex number is always going to be the magnitude times the cosine of the angle. And the imaginary part of any complex number is going to be the magnitude times the sine of the angle. All right. Those are all clear and important relationships that we got to know. All right, so all that stuff is sort of summarized there in one place. That takes us back to where we did end the other day, and I want to pick up with this example. Okay, I said basically there's all sorts of ways that the whole complex number thing gets to be useful for us, and it really gets useful when you get into you begin to see the usefulness of it as you go through in circuits 2 and 2112. All right, and you probably haven't gotten far enough yet in 2112 to see the value of it, but you will. All right. There are two types of problems that this kind of helps with. Okay. The first is where I have some kind of calculus that involves an exponential and a trig function. And the second kind is where I got two trig functions multiplying each other like that. Okay. Now, you know, if you were to do an integral of e to the x cosine x, that integral is an integration by parts. It's the one you need to do twice, right? Cosine sine, you probably have to do twice. I don't remember that one. But when you get these sorts of things, there's basically two ways of trying to simplify them. If I see this e to the x cosine x, what I do is I use my Euler's identity to say that this is the real part of some exponential. All right. And similarly, we're going to do here in a second, if I have a cosine times sine, I use those other two relationships that come from Euler's identity. All right, to try to simplify it. Okay, so we're going to do examples of both of those two things today. All right, now, just to bear with it for a second, if I have, where do I want to do this? I need some space here. All right, so I'll just do it here, right? So if I've got e to the 3x cosine 5x, like that. Okay. When I see that, and I see a cosine, that tells me what I want to do is I want to get this express this as a real part of something. So I want to express this as the real part of something. All right. Now, if I see a cosine 5x, what is cosine 5x going to be the real part of? E to the j 5x. Okay. Now, what gets confusing for people, e to the 3x, this guy is just like a constant in front of this, right? He's just like a multiplier. So in fact, I could, if I wanted to, I guess put the e to the 3x outside like that. Except e to the 3x is just a real number, isn't it? Right? That's never going to give me anything problems. So I'm just going to say this guy is the real part of e to the 3x, e to the j 5x. Now, I said the other thing that's probably important for us is to remember how to deal with exponential functions, right? This guy is just e to the a times e to the b, right? If I have e to the a times e to the b, what is that? E to the a plus b, right? So I can just turn this into real of e to the 3 plus j 5 x, like that. Okay. Now that I use, I guess I'll call it this way, real of e to the ax, like that. Okay. Now, what I was suggesting here on this other slide is I said, all right, well, if I have an integral, right? If I have an integral of something like e to the x cosine x, what I do is I get that expression into this real part or imaginary part form, right? And then I do the calculus operation on the complex function. I forget the real part. So in this case, when I say on the complex function, what I mean is the calculus would be done on the e to the x plus jx. All right. And then I take the real part of the imaginary part as appropriate. Okay. So in this case, I'm going to do my calculus on this guy. So I do my calculus on this guy, e to the 3 plus j 5x. when I'm done, take the real part of the result. The one thing I think that may be confusing for you guys, right? I don't want as an answer that it's the real part of 1 over 3 plus j5 times e to the j. I don't want that. What I want to know is somehow if you did integration by parts, this guy would come up as a trigonometric function. So I want a trig function at the end, right? So there's the other step, which maybe I guess I didn't stay out here, is I want the real or imaginary part as appropriate, and I want it converted back into whatever form it should be in, right? So that's the part we want to figure out now. So basically where I got this guy to is I said this is the same as the real part of the integral of e to the 3 plus j5 x dx. Except it's clunky to carry that whole thing around. So I'm just going to say, all right, this guy, let's do the integral of e to the 3 plus j5 x dx. Right? What should that be? All right. All right, Mr. Engineer, I'm going to take you offline because I know you know this one. I like that name. All right. 1 over 3 plus j5 times e to the 3 plus j5 x plus c. All right. Now the whole plus c is clunky. I'm going to bring that in at the end. Right, as ugly as it's the real part of it. I can just add a constant in at the end, right? So that's what I'm going to do. Okay, that's perfectly fine to do because there's a constant that gets added. There's no reason to say it's a constant times some other constant, right? So I'm not going to mess with it. I'm going to leave it there. The thing is that if I said the real part of that is the answer, that is correct. The real part of that is the answer. But I want you to convert that to a trig function. All right. So how do I do that? Yeah, well, so magnitude and angle, and I got really kind of a couple of different numbers here, right? So first thing I'm going to do, I say I got 1 over 3 plus j5, right? And then I got this whole e to the 3 plus j5x. I could think of that as e to the 3x times e to the j5x, right? All right, e to 3x is a real number. I don't need to mess with him too much more, okay? 1 over 3 plus j5, I want to simplify that down though, right? So when I look at this here, this guy would be some number e to the j5, okay? So I have that a e to the j5 equals 1 over 3 plus j5. And I want you to tell me the magnitude and the angle of that, okay? So I have a e to the j5 equals 1 over 3 plus j5. First thing is, let's take the magnitude of both sides of that whole thing, okay? If I take the magnitude of both sides of that thing, what do I get? Yeah, 1 over square root of 34. Just to be real clear about all this stuff, if I take the magnitude of two complex numbers multiplied by each other, it's the magnitude of a times the magnitude of e to the j5, right? And over here, where I've got basically, again, multiplication, but it's really division, but they're the same thing, aren't they? We use those parallel line bars to denote magnitudes, right? So when I look at that, I can think of it that way. The magnitude of e to the j phi like that, I'm just taking for granted that that's equal to what? 1, right? How do I know that? What's the magnitude of e to the j phi is equal to the magnitude of cosine of theta, or well, I guess I wrote phi, plus j sine phi. How do we get the magnitude of that expression? What's that? Yeah, so it's the real part squared plus the imaginary part squared square root. So what's the real part squared? Well, it's cosine squared plus sine squared, which is 1. Okay. I wanted to make sure that you saw that, right? The magnitude of AE to the J phi, if I think about it, magnitude of AE to the J phi, just to be clear, let's put it over here. Magnitude AE to the J phi is A. Whatever A is. Okay. The angle of AE to the J phi is what? Always. What is this number here, this magnitude? If I put a magnitude in front, what's the magnitude always going to be? What's the magnitude always going to be? It's going to be a real number, and it's always going to be positive, right? So what's the angle of it? So right now so if I think about it, I have one number multiplying another number. So if I say to you, what's the angle of it? Well, it'd be the angle of A plus the angle of E to the J phi, right? What's the angle of E to the J phi? Phi. Whatever angle is up there in that exponent. What's the angle of A? 0. So this is always phi. So when I write AE to the J phi, again, it's there in that summary, right? I don't think it connects with you guys maybe in sort of the right way, right? But when I have R equals A plus JB, maybe I need to make this super clear, right? So the magnitude of this vector is whatever number is in front times E to the J phi. All right, I can add some additional clarification, but I think that's one thing that maybe kind of confuses people. This magnitude right here better always be a positive real number. Okay. Never a negative real number. If it's a negative real number, what's that mean? Negative real number has an angle that's not 0, right? What's the angle of a negative real number? 180 or negative 180, right? Either one is true. Okay. So that's one thing to bear in mind here. So if I look at this guy basically is saying I got two equations here. So there's an equation for the magnitude and there's an equation for the angle when I write this out. So the magnitude of A, right, whatever that is equal to the magnitude of this guy over here, which is 1 divided by the square root of 3 squared plus 5 squared, which is, as somebody correctly said, 1 over the square root of 34. All right. Questions about that? Okay. All right. What about the other thing I guess I have here is there is an angle relationship, right? So if I say what's the angle of A e to the J phi? Well, that's the angle of the other side, 1 over 3 plus J5. So what's that? This guy, the angle of that whole thing should just be phi. Okay. This guy is the angle of the top minus the angle of the bottom. All right. What's the angle of 1? 0, right? What's the angle of 3 plus J5? Now let's think about that. I'm going to use the arctan function here, right? So which do I need to worry about 180s with this guy? 3 plus J5? Nope, he's in the first quadrant, right? So I say this is minus tan inverse of whatever what. 5 over 3. Got it. All right, and this works out to be about negative 54 degrees, something like that. Okay, pretty close to that. All right, so yeah, to here. There's a negative in front because what I have is two complex numbers dividing, right? So it's angle of the top minus angle of the bottom. Yeah, well that's because of the so one thing to remind ourselves of, I guess I wrote this totally in complex form, but if maybe I should add another thing that just, so I think that E to the J stuff messes with your brains, right? when I write what's going on here, I say, well, when I'm dividing two complex numbers, it's you divide their magnitudes, you subtract their angles. When I multiply their magnitudes, I add their angles. Probably would be wise for me to put it for you in polar form as well, which is just a straight up statement of the angles. So to what? Mhm. Yeah, so yes, negative 54 would be this angle points into the fourth quadrant. Sorry, I'm doing it from my direct. The fourth. So well, so let's just be clear. So a e to the j phi, what we just calculated there, a e to the j phi is this guy is 1 over square root of 34 times e to the negative j 54 degrees, or 1 over 3 plus j5, whatever that is, right? Or 1 over square root of 34 angle negative 54 degrees.
We're going to put that on the XY coordinate where
Yeah, because he's got an angle of negative 54 degrees. Anything between 0 and negative 90 is going to be down in the fourth quadrant.
I assume that's going to be 3 and negative 5.
It's going to be whatever. So what I'd have to do if I wanted to get the real and imaginary part, how would I do that? If I gave you this, how would I do it? I'd say 1 over square root of 34, yeah, times cosine negative 54 degrees plus j times sine of negative 54 degrees. Well, I did. So basically, so there's a parentheses around the whole thing. Yes. Yeah. Now that's the downside of me shooting you into MATLAB is that you're not thinking about this as much. You know, back in the days when men were men, we would do that all the time, right? You know, and we, you know, but things have changed, right? So there's a piece of me that says I should make you do it that way all the time, but and women were women too. I'll be neutral on that, right? Yeah. All right, I'm going down the bad path. Not going any further with this. Yeah, but you know what I meant, right? Back. Say yeah. And now I'm putting this on YouTube. That's cool. That's good. All right. Yes. Yeah, because what you're saying is when I have two complex numbers, right? Right. When I divide two complex numbers, the magnitude of the division is I divide, and the angle of the division is you subtract it. That's what I'm doing. What I like about the reason I think of it like this is because I don't need to memorize anything with this, right? When I think of it in polar form, I'm memorizing something. I look at this and say I got an exponential divided by an exponential. I know exactly what to do with it. That's embedded into the brain, and it's never going to leave, right? I don't want to ever try to remember anything. Some stuff just gets stuck. Like back to my point about this thing, right? Where was my Euler's identity? That thing on the top, that's embedded in my brain. Can't get it out. I have to think about the other two, right? That's muscle memory on the top, and there's certain things that should become muscle memory, I think. All right. Now I'm going to see you on the street one day in 10 years, and you're going to be like, "Oh, what do you thought? What's Euler's identity?" You're not going to remember it. At least until you graduate, that top one should become muscle memory. All right. All right. So where were we? We were focused on this guy. We got to this whole thing. All right. Now that was not quite what I wanted to fully cover. What I got was this. We had e to the 3x times 1 over the square root of 34. An angle of negative 54 degrees. And that was all times e to the j 5x. Okay. Now, I look at that and I say to myself, what's the real part of it? I already know, but you don't. So let's see. I'm going to say e to the 3x over the square root of 34. Anytime I have, e to the j something times an e to the j something, what do? I combine those, right? Becomes what? E to the j, what up here? Yeah, 5x minus 54 degrees. Okay. Yeah, so you get the j terms together. Thing we're looking at, I get the stuff with the j's together, that's going to become a trig function. I'm always looking to get the stuff with the j's together, that's going to become a trig function. All right. Now at this point, I'm perfectly happy to do this slowly, right? I can take that. How do I expand this guy here with Euler's identity? I got e to the 3x over square root of 34. How do I expand that with Euler's identity? Yeah, so the e to the j 5x minus 54 degrees, that's basically, this guy's theta, right? Right? So I can say e to the j theta is cosine theta plus j sine theta. So this guy becomes cosine of 5x minus 54 degrees plus j sine 5x minus 54 degrees. Like that. Now, the real final answer we said was, all right, well, we started out with this guy. We said that's the real part of the integral of e to the 3x e to the j 5x. Now, that means it's the real part of the result. When I say it's the real part of the result, it means it's the real part of the thing right above this. So what's the real part of that? The cosine term. The cosine term is the real part. So I say this is e to the 3x, e to the 3x divided by the square root of 34 times cosine 5x minus 54 degrees, like that. Now I say plus a constant. Okay. Now in your homework, I say, well, you need to make a graph of that. Well, what you do is you look at the times, right? Whatever times I tell you to do, and then this is the guy that you plot. And I tell you make sure that your c is equal to 0. Right? Because otherwise you can't have the plus c. Yeah.
So,
Number 4. Or sorry, number 7. Number 7.
the previous equation, the previous problem, if it had a sine instead of a cosine,
You do the same thing except the imaginary part. You do the imaginary part. If you think about it, if I had said, okay, he's asking a good question. If I gave you let's say instead I gave you e to the 3x sine of 5x, you would have done all the same stuff, and you would have gotten to this result, and you would have told me it was the sine term. Okay. What's that? Well, so if I'd given you this, you would have said, all right, well, this is the imaginary part of integral e to the 3x e to the j 5x dx. If you combined that, right, you would have been doing all your calculus on the same complex number. And that would have led you to the same result. And you'd say, well, give me the imaginary part of the answer. Well, the imaginary part of the answer is everything that multiplies the j. So that'll be just the sine term. So it'd be e to the 3x over square root of 34 times the sine. Right? Yeah.
Can I remember to graph that and then the positive phasor and the negative phasor?
No, so you would get to this result here and you'd plot that. Now you could do that, and I had that Mr. Engineer left, but he talked with me about this yesterday. He was plotting like the real part of you could plot wherever it started, the real part of this result. You could do that. But like, for instance, you look at the test, on the test, I'm asking you to take that all the way back to a trig function. So you might as well get yourself able to get it to this. Right. Now, at the end of the day, is this useful? No, it's not, right? Your boss is never, you're never going to be a Duke, and your boss is going to say, the grid's going to collapse, integrate this thing, right? That's not going to be the solution. But what's important about this is a good exercise, right, for trying to get yourself comfortable with complex numbers. You can do this kind of problem, you're getting comfortable with complex numbers. Okay. All right. Now let's look at this guy. Sine of 3x, cosine 4x. All right. This one, I said, this is one where I got that approach number 2, right? Where basically what I do is I say, all right, I want to convert that trig function into each of the trig functions into something I can get from Euler's. Then I'm going to do my calculus operation on whatever complex function results from that. And then I'm going to convert that back to trig. Okay. All right. So let's do that. Sine x, cosine 4x. So I'm going to write down here for us the two things that unfortunately have become burned into my brain. But they were not definitely when I was an undergrad. Cosine theta is that. Sine theta is this. And there's a minus sign there. Okay. All right. So what I want to do is expand the sine and expand the cosine using those two things. So help me out with that. How do I do sine of 3x? What do I write for that? Well, it's 1 over 2j, right? Theta, what's theta? If I'm looking at sine of 3x, what's theta? 3x. So e to the j, 3x. All right, so then it's minus 1 over 2j, e to the negative j, 3x. All right, so I'm done with that. What do I do with the cosine? Same thing, so 1/2. It's less imaginary, right? So e to the j 4x. Yep. Plus 1/2 e to the negative j 4x. Now what I do is I FOIL that out, right? I multiply that out. Now what I'm going to do is I'm going to be judicious about how I make my choices here. I'm not so normally what I would do is I'd say, okay, multiply this one by this one and this one, and then multiply this one by this one and this one. I'm going to do it in a slightly different order. Still going to do 4 multiplications, but I'm going to do it in a different order. Why? Well, because I know something about what's going to happen, I guess. Right? So let's start. Let's do this guy times this guy. All right? What's that going to be? The first two terms. What's that? What's the first term times first term? 1 over 4j e to the j 7x. Right? Then I'm going to do so next I'm going to do this term and this term, the two last ones. Okay, I'm going to do that on purpose. That's going to be, yeah, almost the same thing. Minus 1 over 4j e to the negative j 7x. I did that on purpose. I did it out of order on purpose. We're going to see why I did that out of order on purpose in a second. All right. Now let's do this guy and this guy. Okay. What's that? Yeah, negative 1 over 4j, I got that. And then what do I have for the exponential part? E to the jx. Okay. And we got one left, and that one that's left should be this one, and no, should be, yeah. You shouldn't do it the way I'm doing it. You should do it normally and then reorganize them, right? In the way that I'm about to do. All right. This guy is going to be plus 1 over 4j e to the negative jx. Well, we don't have any canceling out going on. Let's take a look at the first guy. 1 over 4j. Does this in any way, shape, or form look familiar? It looks kind of like this sine function up here. Yeah. Kind of, right? In which way? What would theta have to be here? 7x, right? Couldn't I say this is 1/2 times 1 over 2j, oops, e to the j 7x minus 1 over 2j e to the negative j 7x, right? What is that equal to? That would be 1/2 sine of 7x, right? 1/2 of sine is 1/2 times 1 over 2j e to the j 7x minus 1 over 2j e to the negative j 7x. Like that. Okay, so it's a pattern recognition thing going on. But again, this is just an exercise in trying to get familiar with all these different functions. Okay. All right. How about this character? So when I see these problems, the reason I group them this way is because what's going to happen when I do this is I'm always going to end up with essentially one sine and another sine, or one cosine and another cosine. That's basically what's gonna happen when I do this. Okay. So this guy over here, I got to be trying to get it into one of these two forms up here. Well, when I get the j on the downstairs like this, what am I thinking? Well, I'm thinking this guy should be becoming a sine, right? So looking at this, he doesn't quite look like he fits my pattern, but he would if I said minus 1/2 times what? Let's factor a minus 1/2 out of both of these guys. What happens to the first term if I factor out a minus 1/2? Comes positive 1 over 2j e to the j x. And what happens to this character? Yeah, it becomes a minus 1 over 2j e to the negative jx. All right. This is like a, I don't know, it's like a math Olympiad sort of question of some sort or something to you probably, right? I'm not, it's the kind of thing that you're sort of looking at it by inspection and kind of seeing that it fits one of these patterns. What's this guy here? What's this become trigonometrically? Well, minus 1/2 sine of x. Yeah, minus 1/2, because I got that minus 1/2 floating around. So that tells me this guy, minus 1/2 sine of x is 1/2 times 1 over, or sorry, minus 1/2. All right. So that tells me when I put those two guys together, that tells me that, what did I have? What did I start with? Sine of 3x, cosine 4x becomes 1/2 sine of 7x minus 1/2 sine of x. Okay. Now, if I was saying to you, and I didn't focus on it this way, but if I said, well, give me the integral of that whole thing. So integral of sine of 3x cosine of 4x. I don't know, there's probably some trig identity thing or something that you used. I don't know, maybe it's parts. I don't know which one. That's saying that this guy is the same as the integral of 1/2 sine of 7x dx minus 1/2 integral of sine of x dx. All right. And then it's pretty straightforward from there. right? You should know the integral of sine. I mean, you should know the integral of sine and cosine. All right. Okay. All right. That's all I wanted to cover. I will stop here. If you guys have questions, I can hang out here for another 20-ish minutes or so if you guys want to ask questions.